So this video mostly covers derivatives, which seems like it's going to be the most straightforward, but realize that maybe you're not using the most efficient method, right? So let's take a look at how we can find the most efficient method to find a derivative, because this could save you a lot of time on an exam. The first thing I want to take a look at is understanding the difference between finding a limit using L'Hopital of an exponential function and then comparing it to log differentiation of an exponential function, because often those two methods are confused. Once I go over that, then I'm going to go over some shortcuts of derivatives. Not really shortcuts, but making sure that you're not using the long way to calculate the derivative. We want to take the natural log for both, so let's take a look at what happens here. So here I see that with inspection I get infinity to the zero, which is in indeterminate form. So we have to go ahead and take the natural log of each side, because eventually we know that we want to do L'Hopital, and if we're going to do L'Hopital, then I need to get the form to be either infinity over infinity or 0 over 0, and right now I have an exponent. So the first thing I'm going to do is set y equal to it so that I can take the natural log of each side. And by law of exponents, I could bring this down. By inspection, we have 0 times infinity. 0 times infinity is another indeterminate form. So what we want to do is manipulate this so that we get 0 over 0 or infinity over infinity, right? So I'm going to manipulate it more and bring something into the denominator. Now we have infinity over infinity, we're ready to do L'Hopital. What we're doing here is we're finding the limit. Every single step here is equal to each other on the right side. Therefore, every single step on the right side is equal to ln y. So we do not do implicit differentiation here. We don't do the left side as 1 over y times y prime. That would be finding the derivative, and we're not doing anything like that here. We're just finding the limit. The point of the 1 over y times y prime, which we'll see in the next example, is to implicitly differentiate when we're doing log differentiation. Right, but here we're just trying to find the limit, so we're not doing any derivative at all. We're using L'Hopital, which involves taking the derivative of the numerator divided by the derivative of the denominator, and then taking the limit of that. But it doesn't mean we're differentiating each side. So now I go ahead and do L'Hopital. I leave the left side alone. The left side is untouched. It's just always ln y. And now when I try inspection, I just get 0. So this equals ln y, so that we know when I take each side, I get now that the limit is 1. And that's how you would find a limit with an indeterminate form that's an exponent. I'm going to take the same function now and take the derivative of it so we could see the difference. So you really want to ask yourselves, are we trying to find the limit? If so, that ln y stays the same throughout. Or are we trying to find the derivative of this exponential function? Here I have an x in both the base and the exponent, so that tells me to use log differentiation. If you're confused as to why we're using log differentiation, then go to the derivatives of exponential function video and see it there. Okay, but here we have to do log differentiation. So now, same thing here. I take law of logs. I can bring the exponent to the front to simplify, because again, we want to get rid of exponents. This is the only part that's the same with the two methods. Often these two methods get confused between, but realize here that these are the only steps are the same. The first step and the second step. Taking the natural log and bringing the exponent to the front. Because exponents often make it hard to find limits and to find derivatives. So yes, the first step is the same with taking the natural log and bringing that exponent down. But after that, it's two completely different methods, right? We don't write 1 over y prime here. We don't find the limit here. Okay, they're two different methods: limits, derivatives. L'Hopital, log differentiation. So now we're ready to go ahead and find the derivative. Because we don't have y equals, we have ln y equals, we have to implicitly differentiate. So that's why when I take the derivative of ln y, it's 1 over y prime. So it's important to understand how we get that 1 over y prime, because if you understand that, then you won't mess it up over here. Right here, we're not trying to implicitly differentiate the equation, we're just trying to find the limit on the right side, whereas here we want to implicit differentiate the whole equation. Now I take the derivative of the right side, there's no y, so I just take the derivative normally using product rule. And so now I could bring the y over to the other side, simplify this right side. So now I just have to get rid of the y, and I plug y equals x to the 1 over x in. I combine these two into one fraction because they have the same denominator. I plug y equals x to the 1 over x in, and now we have our answer. So as you can see, two very different methods. They're both the same exact exponential function. Here we're finding the limit of it as x approaches infinity. Here we're taking the derivative. The first step is exactly the same. We're taking the natural log of each side, and then by law of logs, we bring the exponent down. Everything after that is different. So here, we could see the difference between them. As I mentioned in the derivatives of exponential function video, if we have a variable in both the base and the exponent, we have to go ahead and use log differentiation. There's no other option. So this is one way we could see log differentiation. The other way we could see log differentiation is if we have a lot of quotients, products, and exponents. Because we know with quotients, products, and exponents, we could go ahead and use log differentiation, because when we use log differentiation, we take the natural log, and then we could use law of logs to simplify, and those law of logs will work very well with products, quotients, and exponents. So whenever we see a combination of a lot of products, quotients, and exponents, we should go ahead and apply log differentiation. In this case, it's not required, like this case. However, we're going to have to do product rule, quotient rule, and chain rule, and it's going to get really, really tedious. So you don't want to do it that way. You want to just use log differentiation, even if it doesn't specify to do so. Right? You're going to be wasting a ton of time if you go ahead and just apply the derivative normally. So again, if you see like a lot of products, quotients, and exponents, go ahead and do log differentiation. So we take the natural log of each side, then we go ahead and use law of logs to split this, right? This is broken out by a product, so we could go ahead and split by addition. Then I have a quotient, so I could go ahead and split by subtraction. So now, I often see students just go ahead and implicitly differentiate on each side already, but what's the point of log differentiation unless if you can make it really, really simple? We still have exponents here, so why not use all the possible law of logs that you can come up with to simplify this function even more before taking the derivative? Otherwise, you only simplified halfway, which defeats the purpose of log differentiation. So what you want to do now is take the exponents and bring it to the front of each log. We have x to the 1/3, so the 1/3 goes in the front. Here we have a 5, so that goes in the front, and now it's much easier to take the derivative of that, so we could implicitly differentiate each side. The derivative of 1/3 ln x is 1/3 times 1 over x. The derivative of ln sine x is the derivative of the inside, which is cosine x, times 1 over sine x. And then here, the derivative of ln of 2x plus 1, the derivative of the inside is 2 times 1 over 2x plus 1. Both of these are using chain rule. So again, much easier than taking the derivative of, say, ln of 2x plus 1 to the 5th, because you have to do chain rule, it's going to get tedious, and you're going to have to do some simplification. It's going to get really ugly. So go ahead and bring those exponents to the front and use your law of logs. Once we're done with that, we bring the y over to the other side. We replace the y by the original function, and then I just simplify. I can combine the 1/3 times 1 over x to one fraction, 1 over 3x. Cosine over sine is cotangent x, and then I combine this, and I get 10 over 2x plus 1. So again, here log differentiation is required. There's no other option. That's the only choice. Here, log differentiation is optional, but I highly, highly prefer that you go ahead and apply log differentiation. Otherwise, it's going to get really, really tedious, and chances are you're not going to get the correct answer because it's going to get that tedious. Let's go ahead and take a look at some very, very basic derivatives. You're going to look at them right now and think this is ridiculous that we're reviewing this, but often, so often, I've seen on quizzes and exams that students are taking the long way. So let's just make sure that we're using the quickest way possible to take these simple derivatives so that you're not wasting all this time on the final. So the derivative of y equals 3x is obviously 3, right? This function is listed as 3 times x, but we don't go ahead and use product rule because we have a 3, which is a constant. So anytime we have a constant coefficient, we take that 3 and multiply by the derivative of x, right? So the derivative here would just be 3 by that constant multiple rule. Same thing if we had something like y equals 3 sine x, we don't go ahead and apply product rule. You can if you want to, you're just going to be wasting time. So go ahead and take that 3 and multiply by the derivative of sine x, which is cosine x. So the answer here is 3 cosine x. The next example, I often see quotient rule used because we see a quotient. But if you have a constant, if the whole numerator or the whole denominator is constant, there is absolutely no need to go ahead and use quotient rule. Here we do not need to use quotient rule because I can rewrite this. Y equals x over 3 is the same as 1/3 times x. So now when I take the derivative is just 1/3. I saved myself a ton of time. Don't even need to use quotient rule. Same thing with the next example. Again, anytime the denominator is all constant or the numerator is all constant, we just go ahead and manipulate the function a bit to try to find the derivative in a much easier way. We do not have to use quotient rule. This fraction is the opposite of this one, so here I could see that I could rewrite it with the negative exponent. This is the same as 3 times x to the negative 1, and now I just go ahead and use power rule. Again, you can use quotient rule, you're just wasting your time because a simple derivative like this might show up a lot on an exam, and if you do quotient rule 10 times when you didn't even have to do it for any of them, that could really waste a lot of your time and a lot of brain cells, right? Because this exam is a 2.5-hour exam, so you don't want to waste your time doing quotient rule an extra 10 times if you can help it. Let's look at this one now, a little bit more complicated. Okay, not really complicated, but more complicated than these. Here, again, no quotient rule. The whole entire numerator is constant. So what we could do here is bring the 1 minus x all to the numerator and negate the exponent. This is the same as 1 minus x all raised to the negative 1 power, and now I could just apply chain rule. It's much easier than quotient rule. I take the derivative of the inside, which is negative 1, I pull down the exponent, another negative 1, and then I subtract 1 from this exponent. And now I just simplify. So again, you're welcome to use quotient rule if you want, but try to find ways to do things as efficiently as possible. Here you can just do this so that you don't have to use quotient rule. Now let's take a look at this derivative. It looks pretty simple, right? We could just apply quotient rule, but often students will try to use log differentiation here, which is not wrong. But suppose a function like this is in a curve sketching problem. The reason why you wouldn't want to use log differentiation is because it's not going to be that simple to simplify, and then you're not going to be able to tell where that derivative is positive or negative. So it's much easier here to use quotient rule. The way we could see this is because we don't have enough exponents and quotients and products. We only have a quotient and that's it. Okay, so let's go ahead and try log differentiation here so that you could see what I mean. So the reason log differentiation is not recommended here is because I can't split this log by addition. I can't say this is equal to ln of x squared plus ln 1. That's not a law of log. So I can't bring this exponent to the front. So that's the difference with the exponents. If a whole factor, right, if I'm thinking about like products and quotients, if a whole piece is raised to an exponent, that's when log differentiation is helpful. But here, because I'm adding and subtracting constants to something raised to an exponent, log differentiation is not going to help me because I can't do anything with that exponent. So it helps a little bit with the quotient, but because I only have one quotient out of looking at quotients, products, and exponents, it's not really helping me that much. We want a ton of quotients, products, and exponents, like the previous example I did earlier, with the cube root of x sine x all over the 2x plus 1 all raised to the 5th, right? That was a lot of exponents, products, and quotients. But here we only have one quotient, we have no products, and the exponents don't count because it's not like it's only being multiplied and divided by stuff. We have adding a constant, and so we can't, if I add a constant to it, I can't bring the exponent to the front now because law of log says we can't do that. So again, continuing with log differentiation, knowing that this is not the most efficient way because it's not going to help us keep our answer simplified. So I implicitly differentiate here. I get 1 over y prime equals, by chain rule, 2x over x squared plus 1 minus 2x over x squared minus 1, and then I bring the y over and plug in, and I get this. So sure, I could do a little bit more work here to simplify. It looks like it's going to be very complicated to simplify, though. So if I gave you this as a curve sketching problem and you had to take the derivative of it, well, this is the derivative. How are you going to tell where this is positive or negative? It'll take you forever to plug in values, right? We want to plug in some simple derivative so it's easy to tell whether it's positive or negative. So this isn't helping us. There's not enough products, exponents, and quotients for log differentiation to be worth it. Even if it doesn't take that much time to do, it's not worth it here because it's not the most simplified version, and this won't help us when we deal with applications like curve sketching or L'Hopital or anything like that, right? So log differentiation, not really ideal here. So now let's go ahead and see quotient rule. Again, you can do log differentiation. It's just not going to be easy. It's not going to be as easy to simplify, especially if it's like in a curve sketching problem, you want to find the sign of f prime. So that's why we turn to quotient rule. Quotient rule often makes things easy to simplify, which is what's nice about quotient rule, right? So in the previous examples I showed you, where either the whole numerator or denominator is constant, we want to avoid quotient rule because it's going to take a little bit longer, right? But when we have a variable in the bottom and the top, we might want to use quotient rule because quotient rule typically simplifies nicely. Right, so let's simplify a little bit further. So I'll go ahead and distribute in. So I multiply 2x by x squared minus 1, and I get 2x cubed minus 2x, minus 2x times x squared, minus 2x times 1. Now we could cancel out the 2x cubes, and we're just left with negative 4x over x squared minus 1. Much easier to simplify. So quotient rule is nice because it's very easy to simplify, but you want to know when it's going to be ideal to use it and when it's not. It's not going to be ideal if the whole numerator or the whole denominator is constant. And it's also not going to be ideal when you have a lot of products and exponents within that quotient, right? That's when we would want to use log differentiation. So again, most of the derivative techniques in this video, you could use several methods. I'm just trying to teach which one's the most efficient.